Hello and welcome to this demonstration. Here I am going to demonstrate about implementation of Video Mixer in ZedBoard with HDMI interface. Video Mixer IP is one of the Xilinx Logic Core IP cores. It provides a flexible video processing block. It supports up to 9 layers including one main layer and 8 overlay layers. Video Mixer has multitude of features. For example, alpha blending, scaling feature. For more details, we can visit its product guide. ZedBoard is a complete development kit for designers interested in exploring designs using Xilinx Jinx 7000 all-programmable system on chip. This board contains all the necessary interfaces and supporting functions to enable wide range of applications. For more details, we can visit its website. ZedBoard has ADV5711 IC for HDMI interface. We can use these lines to connect our video stream. Then this IC produces TMDS signal which goes to HDMI connector. However, we have to configure this IC to work. This will be discussed in SDK part. In this project, we are implementing Video Mixer on ZedBoard, where one test pattern layer is overlaid to master test pattern layer. That is, one TPG forms stream layer while another TPG forms master layer of Video Mixer. We pass this video stream through a series of video processing IPs and then pass to HDMI interface to lead this video stream all the way to HDMI output monitor. So we will be able to see the corresponding output. This is the entire block diagram. Here, this is the Jinx processing system, so we need a software application to work. This is the Video Mixer IP. As we can see, here are two TPG IPs for overlaying one TPG over another TPG layer through Video Mixer. This TPG is connected to S-axis video port, so this IP forms master layer of Video Mixer. While this IP is connected to S-axis video 1 port, so this IP is connected to stream layer of Video Mixer. And finally, stream TPG layer will be overlaid to master TPG layer. Under Video Mixer customization, we can assign number of layers to be overlaid and their interface type and layer features such as alpha blending and scaling. If we enable these features, here we can access these features from SDK function. But currently we have enabled only one layer with stream interface and alpha blending and scaling features. Now after Video Mixer, we do subset conversion. This is because the ZedBoard HDMI interface supports 16-bit data only. So we have to convert 24-bit RGB data into 16-bit data. So by opening its customization window, here we have done manual data width setting. Input data is set to 24-bit and output data width is set to 16-bit. Now the 16-bit video stream from subset converter is fed to VDMA. We run this VDMA in triple frame buffer mode to achieve 60 Hz frame rate. Now we come to access to video converter IP that combines video stream and video timing and then converts access for stream into native video form. This is the video timing controller IP that is configured in generation mode so that it generates the video timing according to video mode selected in the Video Mixer. This will be discussed in the SDK part. Now in this IP we do some modification. Here we need to set the video format in 16-bit form, but we cannot set any RGB video format here. Now the resulting video stream goes to this IP. This IP is made by Avnet. We can visit Avnet website to get more details about this IP. After this, the video stream goes to ZedBoard-HDMI interface. The ZedBoard has ADB5711 IC for high definition multimedia interface. The video lines from this IP are connected to ADB5711 IC by constraint mapping. Meanwhile, this IP is used to configure an initialization of ADB511 IC. This will be done from SDK part. After finishing block design, we can do validate design. There should be no errors, and if possible there should be no any critical warnings. We can even check address editor to see if address mapping is required here. After all these, we need to generate bit stream, for which we have to complete synthesis and implementation one by one and then generate bit stream. After successful bit stream generation, we can proceed to SDK part. This is the SDK part, where we are going to demonstrate about software application. Before we start coding, we must not forget to include all the necessary header files, which will allow us to use different library functions. Initially, we require X parameter header files, and then hardware platform header file. This is the sleep header file. This is not mandatory at all, but we can use its function when delay is required between the cores. This is the header file which will be used for TPG coding, and this header file for Video Mixer. This is the video controller header file, which is one of the header files that is related to Video Mixer and will be used to control video stream in the Video Mixer. This is for VDMA, and this is for video timing controller. This is used for controlling the ZedBoard-HDMI interface. This is a buffer variable named as source buffer. This will be accessed by VDMA for frame buffering. This frame buffer is created in the DDR memory so that we need to access DDR base address. Its base address can be found under X parameter header file. And this is the function prototype for triple frame buffer function. This function is used to run VDMA in triple frame buffer mode. Here we define buffer address for memory mapped layer of Video Mixer. If Video Mixer has stream layers only, then this buffer will not be used. This buffer is also created in DDR memory. If multiple memory layers are enabled in the Video Mixer, then buffer addresses for layer are assigned at layer buffer address with this offset value. For other color format other than RGB color format, we need to set chroma address, for which we define chroma offset address here. Here these are the global variables. At first we have defined the variables for TPG. As we have already discussed that we have used two TPG IPs, so we require individual instance variable. Here we assign instance variable for Video Mixer and assigning instance variable for video timing controller. Here we assign instance variable for video stream. This will be used for setting stream parameters for Video Mixer. Here we define for color format, which will be used to set color format in Video Mixer. And here we define for video timing based on the video mode defined in the Video Mixer. The timing information will be stored in this variable. Here we have defined video modes. Currently here are two video modes to support SD and Full HD. That is 1280 by 720 resolution at 60 Hz and 1920 by 1080 resolution at 60 Hz frame rate. But in this project scenario we have selected this 1080 video mode. And finally we define for ZedBoard-HDMI display. Here we have defined layer window parameters. This will be used to display a layer within this window frame when layer is enabled in the Video Mixer. Here we see four window parameters. First two parameters represent the location or the position of layer in X and Y coordinates, while following two parameters are width and height of layer respectively. Here we have defined window parameters for 8 layers that is supported by Video Mixer, but we use only one layer, so this window parameter will be used to display TPG stream layer. Now let's go to main function. First, we have to initialize ZedBoard-HDMI interface, for which we configure XCI2CIP. So first we get this IP base address and then passing to this function. Inside this function, XCI2IP is used to configure ADV5711 IC, and then HDMI interface is started. We do initialization of all the IP drivers here. When we go inside this driver initialization, we can see initialization of all the IPs one by one. This is the initialization of BTC IP, and here we see initialization of TPG IP. Here both the TPG IP are initialized. We can even see their respective instance variable. Here we have initialized the Video Mixer, and finally we have initialized XC-VDME. These lines of course are used to initialize the VDME. When all the initialization of IPs are successful, then success status will be returned. If any of initialization is failed, then failure status will be returned and our code will not be executed further. After successful driver initialization, we use this function to get master layer color format, and that value will be stored in this color format variable. Here we see video stream instance variable, which we have already discussed in the global variable declaration. In order to set output video mode and resolution of Video Mixer, we need a pixel clock, video color format, frame rate, and this thing we do here. First of all, we get pixel clock, which is according to pixel clock set in the master TPG IP, and we get the video format, which is stored in this variable. And here we set the color depth value, which is based on the maximum data width values we set in the hardware. Now we set the Video Mixer output video mode. As we have already discussed, we have used modes to support two output video resolutions, 720 and 1080 resolution at 60 Hz frame rate. For the project demonstration, we have selected 1080 resolution, so that we have assigned video mode array index 1 that refers 1080 resolution. And finally, this mode is assigned to this variable video mode ID. Based on the video mode ID, this function returns video mode timing information and then is stored in this timing pointer variable. Now this timing information is used to share the timings for output video mode of Video Mixer IP, and we also get the frame rate for the video mode. After here we have obtained video resolution, timings, and frame rate for the Video Mixer output stream. Now based on these parameters, we do following configurations. We can go inside this function . Inside this function, we take Video Mixer video timing information to configure the generator VTC IP to generate timing information regarding the video mode selected. All these cores are written to assign individual video stream timing parameters, for example horizontal and vertical timing parameters, to this timing variable. After getting all the timing parameters, this function is used to configure the VTC IP based on this variable. And after that we enable generation. So now VTC IP starts generating the video timing signal. Now we need to do configuration of video mixer. Here we send the video stream as parameter. We can go inside this function. We first do disabling all the video mixer layers. By using this function, we set the input and output video resolution for video mixer. This is done according to video stream parameters. Here we do setting the buffer addresses for memory layers. For loop statement is used to assign addresses for all the memory layers. However, buffer address is assigned only if there are memory mapped layers enabled in the video mixer. Our current project scenario has a stream layer only. Therefore, we don't have to do this. We can even remove these lines of code. However, this function checks whether there are memory layers only. After that, we set background color for master layer. We can set different background color with color depth. But currently background color is set to blue color and the color depth value is stored in this pointer variable. The background color is set because when the master layer of video mixer is disabled, then the background color will be displayed instead of master layer. Now we configure both TPG IPs, where we set TPG height, width, and type of TPG pattern. But here is the thing is that the height and width of master TPG must be same as that of input video resolution of video mixer. And the height and width of the stream TPG must be same as that of layer window height and width. Now after configuration of TPG IPs, we come to run VDMA in triple frame buffer mode by executing this function. We get corresponding messages depending upon the success or failure status. Now finally we run the mixer to work in real time. Inside this function, we enable master layer and then enabling all the layer by using for loop statement. We set the layer window so that layer is displayed within this window frame, and all the window frame parameters are defined here. And we can set the alpha value by using this function, where we can specify alpha value within the range from 0 to 256. If we set 0 to this, our stream layer becomes completely transparent, and if we set 256, the layer becomes completely opaque. And entering any value within this range, the layer becomes some degree of transparent. Now we can also set the scaling factor to our layer. By using this function, we can set different scale to our layer. Currently the scaling value is set to this value, so that the layer is scaled to 1 by 1. And finally we do layer enable. After that we have to build our project, for which we can go to Project Explorer and clicking our project and doing a right click, and we can go to build project here. After a successful build project, we can now launch this SDK into our hardware. But before that we have to do bitstream programming, where we can go to this icon to click the program our board. So we click here to program our board. For launching the SDK, we can go to here and clicking our project and doing a right click, and we can go to run as. Then after we can do launch on hardware. So after that we will be able to see our output on the output monitor. Thank you for watching.